Hi, in this video we are going to talk about this popular interview question, LRU cache design. Cache is a memory which is very close to CPU, has very less access time, means it's fast, but small in size compared to RAM. Since cache is really fast, we need to have efficient utilization of the small sized memory. LRU is one of the techniques for this purpose. LRU stands for least recently used. And the concept that LRU uses is called temporal locality, which means the item which is accessed now is very likely to be accessed in near future. In LRU, we keep the recently accessed item in the cache and we remove the least recent items when we need space in the small sized memory. Let's understand the concept of LRU with this example. Let's say our cache size is 4 and we have these items which are accessed one by one. So initially cache is empty and when you access 10, it's not there in the cache, so we have a miss. So when something is not there in the cache, we call it a miss. And if you are accessing something which is already there in the cache, we call it a hit. So 10 is a miss, we insert it into the cache because all the 4 slots of the cache are empty. Now we access 20, we insert 20 also into the cache because we have empty space. But notice that I have put 20 before 10 because in this example, I'm maintaining this order that the most recently used item is at the front and least recently used item at the back side. Now when we access 10 again, 10 comes to the front, right? It's a hit, 10 is present and it also comes to the front because it's the most recently used item. Now when we access 30, 30 comes to the front and these two items go to the back in the same order. 20 is the least recently used item here. Now when we access next item 40, 40 comes to the front and these items go to the back side in the same order, right? 30, 10, 20. Now when we access 50, we need to create space for inserting 50. We want to insert 50 because 50 is likely to be used again. That's the concept we are using. And since we are inserting 50, we need to have an extra space for this. To create extra space for 50, we remove the least recently used item 20, which is last item. So when we remove an item, we always remove the last item because we have written the items from most recently used to least recently used. So we remove 20, we put 50 at the front, right? And put these 3 items in the same order. Now when we access 30, 30 is already there in the cache, but 30 comes to the front. Now when we access 40, 40 is already there in the cache and comes to the front. When we access 60, we see a miss and the cache is full. So we need to remove an item. We'll remove the last item 10. We'll put these 3 items to the back side and bring 60 here. Now when we access 30, it's a hit. 30 is already present in the cache, but we bring it to the front and move the 3 items to the back side. So this is the functionality of LRU algorithm. In this LRU design question, we need to design a data structure that supports these operations. You are given a capacity internally. When you refer an item, if it's already there in your data structure, then you mark it as most recently used. And if it's not there, and if your cache has empty space, then you insert it and again mark it as most recently used. And if it's not there and your cache is full, then you need to remove the least recently used item and insert this item and mark it as most recently used. Now please pause this video and think of a data structure design that supports these operations in the most efficient way. Let us first talk about a simple implementation, which is simply use an array. So whatever we have shown, we have an array of size 4 and we do these operations in the same way in an array. But what will happen if you use an array? Your hit and miss, both cases will have big O of n time complexity. Because if you want to see a hit, you need to traverse through the whole array. In the worst case, then you will figure out whether this item is present already in the cache or not, right? So in worst case, item would be present at the last position and your hit is going to take big O of n time. In case of miss, anyways you will traverse through the whole array and then you will figure out it's a miss and then you will insert this item at the front of the array and then you will move the n minus 1 items one position back. So both the operations are big O of n. Now please pause this video and think of an implementation which has both these operations in big O of 1 time on average. Let us now talk about an efficient implementation. If we take a closer look at this problem, we can notice that we need a data structure that can quickly tell us whether an item is already present in the cache or not. Also, this data structure should quickly allow to insert an item. So which data structure has search and insert as fastest operations? I think you must have guessed. The answer is hash table. We use hash table to insert an item if it's not already present in the cache, and we also use hashing to quickly find out whether an item is already present in the cache or not. Now the question arises, how do you maintain this order of recency? Because hashing is unordered. There is no order maintained among the items in the hash table. For that purpose, we use a doubly linked list with hashing. Let us now see the working of efficient implementation. We are using two data structures here, hashing for quick access and insert, and doubly linked list to maintain the recency order. Also, doubly linked list allows us to take out a middle item and move it to the front. Because when you access an item and if it's already there in the cache, then you want to move it to the front to make sure that it goes to the most recent item. It goes as a most recent item. Let's see the working with this example. Say we initially have empty cache and we now access 10. When we access 10, we create a node in our doubly linked list. We get the reference of this node, reference in Java and address in C++, and create a key value pair in our hash table where key as this 10 and value as address of this doubly linked list node. We'll soon see the advantage of storing this reference or purpose of storing this reference. When we see 20 next time, it's a miss. It's not there in the cache. So we create a node in doubly linked list and insert 20 at the front of doubly linked list and store its reference or address in our hash table. Now when we see 10, we look up into the hash table and 10 is already present in the hash table. So we do not make any change to our hash table, but we make changes to our doubly linked list. We take 10 and move it to the front. Now how do you move an intermediate item to the front in doubly linked list? You use the hash table. Using the hash table, you find out the reference of this node, right? And you reach this node and then you can remove it from the middle. Because it's a doubly linked list, you can remove a middle node from this if you have reference or pointer to this node. So you remove it from here and then add it to the front. And that's the reason we store these references, so that we can take a middle item and move it to the front. Now when we access 30, 30 is not present in the cache. So what we do is, we create a node in doubly linked list first, right? And insert it the head. So whenever a miss happens, it always goes to the head. And whenever a hit happens, then also an intermediate node goes to the head of doubly linked list. So it's a miss. A new node is inserted always at the head. And say R3 is the reference of this new node. This mapping is inserted into the hash table. Now when you access 40, 40 is also a miss. So you are going to insert a new node at the head and insert an entry 40R4 in your hash table. Now when you access 50, 50 is also a miss. And this time you need to remove a node from the linked list and from hash table as well. So which node you will remove? For that purpose, you will maintain a tail pointer in your doubly linked list, and using the tail pointer or tail reference in Java, using this tail reference, you will always remove the tail when your cache is full, right? So using the tail pointer reference, we'll reach this node. We'll figure out that this is the node to be removed, and we'll remove this node and we'll insert this new node 50 at the front. So we have removed it by using the tail reference or pointer, and we have inserted 50 here. And when we inserted it 50 here, we entered its entry 50R5 also. And we deleted its entry from the hash table. 20 and R4 is removed when you accessed 50. Now when you access 30, 30 is already there in the hash table. So we are not going to make any change into the hash table, but in doubly linked list, we are going to bring this 30 from here to here. And how do we bring it from here to here? We use the reference here, R3. Using R3, we reach here, we delete it from here, and then we insert it here, right? And this is all possible in big O of one time in a doubly linked list, removing the middle node if you have reference or address of this node. Let's now process our next item, 40. When we process 40, it's a hit. 40 is already there in the cache. So what are we going to do? We are going to move 40 from here to here, right? And we are going to remove it from here. So we move 40 here, and whenever there is a hit, there is no change in the hash table. Now when we access 60, 60 is not there in the hash table. So we are going to remove the last node using tail pointer or reference. And we are going to insert 60 at the front. And when you insert a new node, you reuse its reference and insert an entry in your hash table. And you remove the entry of the last removed node. Now when you access 30, you see that it's already there. So there is no change in the hash table, but you bring this 30 here, right? At the front, because this is the most recently used item. So in our doubly linked list, we are maintaining this, that the most recently used item is at the front and the least recently used item is at the tail. So basically our doubly linked list works as a queue, but it supports an additional operation that some middle item has to be moved to the front. Here is complete process for referring an item into the cache. When we refer an item X, we first look for X in the hash table. HT stands for hash table and DL stands for doubly linked list. If we found it in the hash table, which means we have a hit, what we do is we find the reference of this node in doubly linked list by using hash table. So we use this X as a key and value gives us reference or address of this node in the doubly linked list. And what we do after that, we move this node to the front of our doubly linked list. If not found, if it's a miss, then we insert a new node at the front of our doubly linked list. So we need to maintain both front and tail pointers in our doubly linked list. After moving it to the front, we get the reference of the newly created node and insert an entry into the hash table with X as a key and reference or address as a value. Now, what are the time complexities in the cases when we have a hit and when we have a miss? When you have a hit, what are you doing? So first of all, to look for X into the hash table, we are doing big O of 1 work because we are looking up into a hash table. And when we have a hit, then we are finding the reference, which is again a lookup into the hash table, which is big O of 1. Then moving the node to the front, which is big O of 1 in a doubly linked list. You are given reference or pointer to a node, you can move it to the front in big O of 1 time. Now in case of miss, you are inserting a node at the front of doubly linked list, which is big O of 1 operation. And then you are inserting an entry into the hash table, which is also a big O of 1 operation. So in case of both hit and miss, you have the time complexity as big O of 1.